Yeah, that's one of the pleasures of working from home, is that you figure out all these noises that you don't.
Yeah. I'll point it again. It's just not hot without that. I don't know where it's coming from, but it's not, it must be a neighbor, so hopefully it'll stop soon.
And we don't hear it, so that I think.
Oh, okay, that's good. Okay, that's good. As long as you can hear me. It's like background. But okay, just let me know when I should start.
Okay, one more minute.
Okay. Are there any, I guess while we're waiting, are there any questions from previous lectures? I posted the notes on the Slack channel. I guess I haven't posted them on the wiki yet.
Nope. Okay, I think we can start. So we're happy to have the third lecture on Introduction to Cosmology, and whenever you're ready.
Okay, thanks. Let's at the top. So, oops, I used the wrong. Intro to Cosmology, lecture 3. So these are clearly going a bit slower than I anticipated, but hopefully it's really clear to everybody because of that. I think based on some of the questions and stuff, I slowed down a little bit, and also just that's how I manage time. So today we will finish our discussion of the smooth universe. And this
No, looks like we lost Marilena's video connection. She's communicating by writing on the screen. So she's rebooting her laptop, it looks like.
Okay, that's fine. Yeah.
The advantage of having 2 separate devices, I guess.
So if you just signed in, we're having a technical glitch that we'll solve in a couple of minutes. Does the iPad have a mic? Maybe you can just turn that on.
I'm not sure if you can do that and share the iPad screen at the same time. At least I don't think we've had anyone try that yet.
Okay, no, that's fine, yeah. I thought that's what Iris had done, but I could be wrong. So there's a comment that this could work.
I don't think her iPad is connected to sound right now, so I'm not sure she can hear us.
Ah, okay.
She seems to be.
Oh, she might still be in
writing
the
something.
Yeah. Can you check if she has to be upgraded?
I've been watching. I have not seen her join yet.
Yeah, that's a good point. She might not, I think she might be looking at the messages on the other. Oh, there she is.
I see. Yeah. Sorry. Okay. I'm really sorry about that. I have a not very old laptop, but if the plug gets knocked out, it crashes and it restarts with the date wrong several years ago, and it takes like several minutes. I'm really sorry about that. I hadn't noticed that I knocked it out.
Don't worry, looks fine.
Okay. So today we're going to finish talking about the smooth universe, expansion history, matter contents, and then we'll use that to start talking. We'll talk a little bit about the thermal history of the states of matter in the universe. And then we will start on cosmological perturbation theory. So, so last time we'd used the background or smooth universe solutions to Einstein's equations and the continuity equation to and a list of the types of matter that exist in the universe that we know about today to reconstruct this energy diagram where we have different types of matter that dilute differently as the universe expands. And so photons and neutrinos, which at early times dilute as A⁻⁴, stuff that has its energy density dominated by the rest mass, dilutes as A⁻�3, which includes neutrinos after they transition to being non-relativistic. And of course, we don't know exactly where this transition is, but we do have some upper and lower bounds on it. And then the weird stuff that's just not diluting at all, apparently, which is dark energy. So let me move this down even further. This given. Sorry. Okay, so we had this, and then we had the Hubble equation for all the stuff that we know exists in our universe, which we write in the following form. Actually, not h naught squared, but 100 kilometers per second per megaparsec squared, and then times stuff that these little omegas. which is a more complicated function of A. We'll write this as, oops, sorry, what does that say? -4, that should be -3. So the non-relativistic stuff that's diluting like that, the relativistic stuff, and then this dark energy stuff that doesn't seem to dilute at all, where there's a little asterisk here that's for. Okay, and then I introduced these distance measures, and these are the ways that people measure the matter and energy contents in the universe at late times. So at late times, meaning for my definition of late times, I mean at times when neutrinos are already non-relativistic. We group all of this stuff together into just a total matter density like this. And this piece is much, much less than everything else. So our Hubble equation reduces to a late time Hubble equation. Where I've written it like this. Now, this equation gives the expansion history, or the expansion rate, h of a. And so from this, you can compute how the things like the co-moving distance will depend on A, given particular values of omega m and omega lambda. You can compute things like that luminosity distance that I mentioned earlier as a function of A, given these values. And then these are things that can be compared to observations. So I imagine you all are mostly somewhat familiar with type 1a supernova data. So the idea here, sorry, I copied these figures, but I'm not giving myself enough space. So I'll move them. Just come back for that. So here people measure the apparent, people call it the apparent magnitude, which is an astronomer unit, which something like the local flux of photons from type 1a supernova. The light curve of a supernova, meaning the flux per time, has a shape where it gets bright and then it gets dim again. And all the different supernovae have different curves. But it is an empirical observation. All the curves, the type 1a supernova light curves are a one parameter family, meaning that there is one parameter that can be used to relate like the time to the amplitude. So these are what's called standardizable. People call them standard candles, but it's really standardizable candles that allow people to determine the intrinsic luminosity. And therefore extract the luminosity distance. So let me move these images down. Apologize again. I suppose I should just draw these, but I thought it would be nice to show. So by measuring supernova with photons with different redshifts, you can infer the redshift of the they infer the redshift of the host galaxy for the supernova, and then reconstruct the luminosity distance as a function of z. And this constrains cosmology, and it primarily constrains joint combinations of omega n and omega lambda from this equation up here. Now, so this, as you all know, led to a big surprise like 20 years ago, that the expansion of the universe is accelerating. And it's not necessarily our best evidence for that today. There's a lot of different kinds of evidence, but given the distances we've discussed so far, this is the most straightforward one. So these are curves from a paper by Skolnick et al. From 2018. And these diagrams, let me zoom in on this one, show joint constraints on omega lambda and omega matter, that total matter density from the supernova data. So this big curve here is the data from 1998 that illustrated that our universe was not flat, in which case omega lambda plus omega matter would be 1, because we don't see any other types of matter around us. And moreover, that the universe, the expansion of the universe is accelerating if you're above this line. So today these data land somewhere around here, which give fairly large contours for omega lambda and omega matter compared to what can be obtained by using a bunch of different data sets together, in particular CMB data. But okay, I just wanted to show you that. And then along with this, so this is assuming whatever this mysterious stuff is, dark energy goes like constant, as in the vacuum energy or the cosmological constant. But in their analyses, they also free that up and allow rho dark energy to be equal to give a free equation of state, so that the pressure of dark energy equals W times the energy density with a constant, so that you can use our equations from before to deduce that the energy density dilutes in this way. So allowing this to be a constant but a free parameter, so that this mystery stuff that we don't know what it is doesn't have to be a cosmological constant or a contribution from pure vacuum energy, is something they do in the analyses. And then they get these kind of big contours where you see W, the best fit values of W are around -1. But it's degenerate with omega matter. Okay, and then I just summarize here this is, you can get much better constraints by combining with other data, but using these supernova data alone, this is the types of constraints they get. So the fractional density of matter in our universe or the fractional density of stuff in our universe that's non-relativistic matter today is about 1/3. If you remove the assumption that the universe is flat, so allowing yourself to be anywhere in this omega lambda omega matter plane, as opposed to on the line where omega matter plus omega lambda is equal to 1, you get numbers that actually don't differ very much for a best fit value. So even allowing a non-flat universe, the best fit value is really close to the flat universe line. So why that extra parameter? And then if they free up this equation of state parameter to allow the dark energy to have some equation of state that evolves with time, they get values that are quite close to -1, which would be the value for the energy density to be constant, as we'd expect for a cosmological constant or vacuum energy. Okay, so we'll talk more about other ways of measuring these, but so far this is to illustrate how some subset of the cosmological parameters that people use to define our universe and refer to as part of our 6-parameter model are determined. On these plots, you can also see that they add, in some cases, they add other data from the cosmic microwave background that really improves things a lot. So we'll talk about that shortly when we talk about the inhomogeneous universe. So now what we've discussed is, so we've so far discussed things like determining the expansion history A of t and H of t, which depend on how the total energy density evolves with A, which depends on the pressure, of course. But now that we know this, we know something about some of the types of matter in our universe, we can go back and try to compute things about what the different phases of matter that existed in the universe in the past. So given that, for instance, the temperature of the cosmic microwave background today, we can compute the temperature in the past, and we can infer that when the stuff in the universe, when most of the photons in the universe had energies at a given value, that allows you to determine what particles were present at that time, because if photons had energies high enough energies to produce pairs of higher mass particles, then they would be present as well in the universe. So we'll do this briefly, and we'll do this as an example of computing the neutrino energy density, which is relevant, and the same calculation can be used to compute the relic density of any other light particle that decoupled from the rest of the stuff in the universe when it was relativistic. So I'm calling this the thermal history. So we're going to compute rho nu of A. This is a nice exercise. So the cosmic microwave background, which overwhelmingly dominates the photon energy density in the universe. Of course, there's photons produced from stars and all kinds of other processes, but the number density of cosmic microwave background photons and energy density is dominant. Actually, there's a really nice chart I'll include in the notes that divides up everything in the universe, computes the omegas of everything in the universe, like stars, different types of stars, dust, and so on. But the local measurements, and these are local, meaning they're measured by the COBE-FIRAS satellite, which was an experiment which was launched in the early 90s. And this data hasn't been updated since then. Determine the temperature of the cosmic microwave background to be 2.72548 plus or minus 0.00057 Kelvin, and in EV, this is 2.3484 plus or minus 0.00049 times 10 to the minus 4 EV. So this data is from 1994. The actual measurement I'm quoting here is from an updated calibration from like 99, but this is really changing things in like the fourth decimal place. The data, they measure this temperature by measuring the full blackbody spectrum. So the intensity as a function of frequency, say. And it is the spectrum of microwave background photons is a black body to an excellent degree. Someone who worked on this instrument once told me that this measurement it's the best measured black body, and it is known that the CMB temperature agrees with the temperature of a black body, like a perfectly black emitter, to a better degree than the actual frequency distribution of the black body curve has been verified experimentally. So we know the shape of this curve. It's 1 over e to the h nu over t minus 1 but the experimental measurements of that are not as good as we know that these two things agree with each other. So it's really beautiful data. Now this, okay, so given this distribution, we know that the number of photons in any, with momentum and position in these, in a little volume of space and a little momentum volume around some central value is given by this, where F is the Bose-Einstein distribution. In this case, it's homogeneous, so independent of X. And we write that F of P is equal to 2 for the 2 spin states of a photon, P over T minus 1. And then we can compute the number density of photons by just integrating this as usual. And if you do this integral, you get, it's easy, one of these practices. It's proportional to T cubed, just dimensionally that's true, and then you get these numerical factors here. If you plug in the H bars and the C's, you get that this is approximately equal to 410.7 per centimeter cubed. So there's a lot of microwave background photons in the universe. The energy density is computed in the same way. And you get, we'll need these numbers in a second, so I'm leaving them out here. Something that's proportional to T gamma to the 4th, and this is about 0.13 eV per centimeter cubed. And P gamma, the pressure, is equal to just P over, P squared over 3E, which for photons is just P over 3, and it's the same thing. So this reproduces the P is equal to a 3rd row that I quoted in last lecture. Now, just a comment about this. So these distributions, this is a black body distribution. And if we derived this from like statistical mechanics or kinetic theory, this would be the distribution of the energy of a system that is in thermal and chemical equilibrium. The CMB is not in thermal and chemical equilibrium today because it's not really interacting with anything at all. These photons are just traveling through empty space, having very little scattering. Yet the form of this distribution is still that of a thermal black body. And that's because individually, what is this distribution? This distribution is telling me that that if I were to measure all of the photons that I measure, all of the photons intersecting some point in a little volume, and I made a histogram of what their momentum distribution is, it would look like that, like the black body that we expect. And so that would give me a histogram of their final momenta. Now I know individually each one of these photons' momenta is redshifting as 1 over A as the universe expands. So, and they're not interacting. So that amounts to taking this distribution function with P equals H nu, and every single one of these all the photons with this momenta, their momenta is a little bit higher at earlier redshifts and a little bit higher and a little bit higher and so on, such that the whole shape of the curve just shifts up. And if you look, which in the form given here is equivalent to just changing the temperature. So temperature has a different meaning here. In some sense, I mean, we say temperature, but it's not like it's it's stuff in thermal equilibrium, thermal and chemical equilibrium. This is, in this case, it's really a parameter that describes this distribution function, which is inherited from an earlier time when the system was in thermal and chemical equilibrium. So just the comment, as we described last time, P is proportional to 1 over A. So for these distributions of stuff that's not interacting, P going like 1 over A is equivalent to sending T going like, oops, sorry, 1 over, what is it? 1 over 3. 1 over A. Okay, so now this is great. We like thermal distributions because this one parameter T gamma tells us everything we need to know. It tells us the number density, the energy density, and the pressure of this stuff. Now we want to do the exercise of determining the neutrino energy distribution. So, so from this, T goes like 1 over A, where this is for non-interacting. For photons not interacting with anything else. So we want to determine, let's say, rho nu and properties, or even F nu. So in the early universe, when temperatures were much higher, then the temperatures were higher and the universe was generally hotter and denser, then frequent scatterings kept neutrinos in equilibrium with everything else that was present. And so, for example, we had electron-positron pairs that could create neutrino-antineutrino pairs. There was just scattering of neutrinos off of electrons. Sorry. There's a scattering of neutrinos of different flavors off of each other, and so on. If you go to high enough temperatures where the typical energy of a photon was sufficient to be able to pair produce like muons and so on, then of course you would have scattering between other leptons and neutrinos here. So in this case, but at these times, neutrinos were in thermal and chemical equilibrium with everything else. Now, as the universe expands and cools, then these interactions become less frequent and they can't keep up. And eventually the neutrinos cease to scatter frequently off of the other particles that are present in the thermal bath at that time. Now, to estimate when that happens, the quantities that you want to compare are the scattering rate of the process that you're interested in, which in this case will be these kinds of processes, neutrinos scattering off of electrons, and compare that to the expansion rate. Okay, so at that point, the interactions would be infrequent. So the scattering rate that we're interested in here, we can write as number density of neutrinos times the cross section, which in this case is just the weak cross section. And then we compare these two things. So if neutrinos are relativistic at these early times, we expect that neutrinos are definitely relativistic at these times. So number density of neutrinos is also proportional to the neutrino temperature cubed. So setting these two things equal to each other gives, on the left-hand side, we have GF T nu to the 5th, and on the right-hand side, we have H, where H at this time is in the early universe. The energy density is dominated by radiation. So H squared looks like rho radiation over 3 Planck squared, which looks like T to the 4th. Like the neutrino temperature to the 4th, because the temperature of everything around is common, but with some numerical factor out front, because I have to sum up neutrinos and electrons and positrons and photons. Divided by m Planck squared. So we then get the question is, should it be GF squared here? It is GF squared. Here? Oh, thanks. Sorry, on this line down here. Yeah, thanks. Thank you. That would have led. Yeah, thank you. Sorry, just a typo. Typo and recopying this to this hand side. So thank you. So this is approximately equal to T nu squared over m Planck. So this gives that the time that this happens at is roughly 1 over GF squared m Planck to the 1/3. And this is around, or I guess, sorry, this is what we want to call this T decoupling. So this is T neutrino decoupling. And this is about an MeV. Okay, and of course you can do the calculation in more detail, but this is a great estimate. It works really well. So okay, so now we know we know the temperature that this happens at. If we wanted to, we can compute the time, but we don't want to do that right now. What we want to figure out is what the leftover temperatures of the neutrinos is after this process. So what we have is that prior to nu decoupling, we have T gamma is equal to T E plus minus is equal to T nu. So because this is at a temperature of an MeV, now I know that there's going to be electron and positron pairs floating around, because the typical temperature of photons is going to be several MeV, and I have this huge tail, and it actually takes quite a while to this is just about the mass, the energy that you need to pair produce these two, but you have a whole huge number of photons, so they actually don't stop pair producing until electrons and positrons don't annihilate and not get regenerated until the temperature is more like tenths of an MeV. Okay, so prior to neutrino decoupling, we have this case. After, analogous to the argument that the momentum of every single photon redshift is 1 over A, and that's equivalent to changing the temperature in that distribution function to something that redshifts as 1 over A, the temperature of the neutrinos will redshift as 1 over A. So that's good. We also have that the temperature of photons and electron-positron pairs also decreases as 1 over A until the time when the universe cools sufficiently that electron-positron pairs are no longer in thermal equilibrium with everything else. So this turns out to happen. You could estimate this, and if you guessed, you'd guess it's around the same time. But if you compute it, you'll actually find that it happens later. The TE plus E minus freeze out happens at around 0.02 MeV. Because of this huge number of photons, there's even if, if you look at a distribution, Fermi Dirac distribution, the peak temperature is about, or the peak momentum is about 3T. And so this is already quite a bit higher than T, which is over here. And then there's just this huge tail. And so there's for a long time, there's a lot of high energy photons that can continue to keep electrons and positrons around. When that happens, this annihilation here injects energy to the photon bath. That energy thermalizes, but it is going to change the distribution of the photons relative to the neutrinos, because the neutrinos don't get any of that energy. Their temperature just keeps redshifting like 1/A. Photons are going to get heated by this, and their temperature will go up relative to neutrinos. So we can compute that in a couple of ways, but the easiest way to compute it is to note that the entropy density is conserved in this process. Oops. So, okay, so we just want to compute this. So we know how to compute this entropy density is overwhelmingly dominated by the relativistic particles. So those are the only ones we have to worry about. We know the energy density of bosons because we just computed that. And it's going to be, we just computed it for photons. In general, it's 2 pi squared over 45 times chi times t cubed. And p is just equal to a 3rd rho. And the energy density of fermions, it's almost the same. We just have a +1 in the denominator of that integral. And this ends up being 7/8 times, so this will be GB, GF times, sorry, that's not t cubed, that's t to the 4th. And the pressure is the same. So the entropy density before decoupling is the neutrinos plus the photons plus E plus minus the entropy density in electrons and positrons. And the entropy density after is just the neutrinos plus the photons. So the electron-positron pairs are gone. So if I use this expression right here, okay, the question is, when saying the entropy density is conserved, do we assume that the decoupling happens instantaneously? So to my knowledge, that the instantaneous decoupling isn't, the conservation of entropy is not related to the instantaneous decoupling. So we assume instantaneous decoupling. I mean, yeah, I guess you're assuming that the decoupling happens quickly compared to the expansion time. So you assume decoupling happens quickly compared to the expansion time, and we're going to assume that this, in our calculation, we'll assume that this process, which happens around 1 MeV, is totally over. Sorry, that the process of neutrino decoupling is completely finished by the time that electrons and positrons freeze out. So that these two processes happen separately, and that's not exactly true, and that'll lead to a slight correction to our answer, which I'll mention briefly. sorry, so the question, the comment is, or we would say the total entropy is conserved, but you think we need to assume that the scale factor is equal during the decoupling. So I think this is kind of a related, I mean, the statement is that the expansion is adiabatic, and that I guess there's a couple of things. The universe is an isolated system, and these processes that are happening here, so electrons and positrons find each other and annihilate, that happens on a fast time scale compared to the expansion time scale. So it's not strictly true that the volume is the same, but that's the limit that we're working in. Does that answer your question? Okay. Okay, so now to do this, so equating these two, then we will get the following. So at this stage, the neutrino entropy clearly is going to cancel from both sides of these because it doesn't change. It's exactly the same. So this is proportional to T nu cubed. Let me use another color so it's not so messy. So this one goes like T nu cubed. And since prior to electron-positron annihilation, all these guys have the same temperature. Every term in this equation goes like T nu cubed. So since they're all in equilibrium prior and after nu's decouple, the T nu goes like 1 over A, as does T gamma Te plus minus. Afterwards, the photons are heated. So we still have S nu going like T nu cubed because nothing has happened to the neutrinos, but the photons will have a new temperature. So their entropy density will go like some other temperature, which will be the final one that we measure today, because electron-positrons are the lightest particles in the standard model, and no other processes have happened that dramatically changed the photon temperature since that time. Okay, so what you find coming up here is, let's add this all up. So the things that we need to keep track of are the factors of 7/8, which comes out of doing those. Sorry, one second. So the factor of 7/8 that comes out of doing these integrals over the Fermi-Dirac, relativistic Fermi-Dirac distribution instead of the Bose-Einstein, and then the different degeneracy factors. So here these G's include spin and then also number of particles, meaning like flavors of neutrinos and antineutrinos and electron-positrons. So there are two questions here. One is, why is the electron decoupling temperature much smaller than the mass of the electron? So I discussed this earlier, right? So the point is that, you would guess that it's around an MeV or a half an MeV, the mass of the electron, but the temperature tells you, the peak of this distribution is about 3 times the temperature. So that already changes your number by a factor of 3. And by the time, this distribution has a huge tail of very high momentum particles. And so it turns out that if you do the calculation, you find that this is much lower. The same thing is true if you guessed naively when hydrogen recombination happens, you guess it's 13.6 eV. If you actually do the calculation, you get something that's more like 0.2, 0.3 eV. There's just a huge number of photons in the universe compared to everything else. So that's question number 1. Number 2, at this moment, is the electron relativistic? The answer is no. And so that's why we're using conservation of entropy. It's easier to compare the entropy well before this process and well after this process than it is to use energy conservation. So in principle, you could use like the continuity equation to do this as well, but it's more complicated because the electron because the electron, around the time that the electrons and positrons freeze out is around the time they're becoming non-relativistic as well. So it's easier to use this, and we can do this calculation. S before can be far enough before that that this computation of the entropy is the right one. Okay. Yeah, okay, and so the following question is, should we use the non-relativistic formula for rho electron? And the answer is no, because, but yeah, so this is a good question. You know, I told you that the overall continuity equation is true for all the stuff in the universe at all times too. So in principle, you can use the continuity equation to compute the radiation density, including the electrons and so on, but it's harder. So in this calculation, we use the fact that entropy density is conserved. And that means we can compute it before, and we can put this before can be well before that transition. So this can be, you know, when they're relativistic, so that this is the correct. But in any case, it doesn't really matter. As they become non-relativist, I mean, this scales like the number density. So yeah, it scales like the number density, which goes like T nu cubed anyways. Good. Does that answer, that was 3 questions all at once. Does that answer those questions? Okay, I will assume so and move on. Okay, so we want to compute the entropy density, and the entropy density before is this gives us S gamma plus SE plus minus. Before is equal to S gamma after, because the neutrino part cancels from both sides. And then we plug in for our expressions that we had above, and we will get we get 2 plus 7 8, 2 times 2, where I'm writing it in this way just to be clear over where everything comes from. So here, this is for the 2 spin states of photon. And then this is for the 2 spin states of E plus E minus. So the extra 2 is for the fact that we have particle and antiparticle pairs. Okay, and that gives, and then the last term is just the entropy density of the photons. So if you do this and you solve it, you will get that T nu is equal to 4/11 to the 1/3 times T gamma. And if you compute this, it's about 1.945 Kelvin, or 1.67 times 10 to the minus 4 eV. So this is a prediction, assuming pretty low energy standard model physics and some basic statistical mechanics. Now, again, just to emphasize, this gives that the distribution, the momentum distribution function for neutrinos is a relativistic, so I'll put for one neutrino, meaning for each flavor or eigenstate, looks like this, where, one thing I want to emphasize briefly here is that this is a relativistic Fermi Dirac distribution. And this is the momentum distribution that they have at the time of decoupling. As the neutrinos travel through the universe, each one of their momenta redshifts like 1 over A, which is equivalent to T nu going like 1 over A. So even today, once the neutrinos are non-relativistic, as at least 2 of the mass eigenstates have to be given this mass, their momentum distribution is still that of a relativistic Fermi Dirac. That is, even though they're non-relativistic, you don't plug in E up here because they're not continuing to have these processes today. This is a relativistic Fermi Dirac distribution that is inherited from early times and preserved as the universe expands, because the neutrinos aren't scattering much. I emphasize that because sometimes people get confused and think that since they're non-relativistic, you should like change the distribution function, but that's not true. If they're not continuing to interact, they don't continue to have a thermal distribution. This is just the initial condition that is preserved as they travel. So given this, so we compute these neutrino properties. We can compute the number density of each neutrino state, and we do that again using the exact same formula. And today, this is about 56 per cubic centimeter. So for each new and new bar state. So, okay, so we now know almost everything that we need to know to compute the neutrinos. We know their number density today. In the early universe, so here I mean at CMB times, and we'll assume that neutrinos are relativistic for now at these times, and the data confirms that. We've known that neutrinos have been non-relativistic since CMB times for 10 or 15 years. And so the radiation density at CMB times is parameterized in the following way. We write rho gamma plus some parameter n effective, the effective, thanks, missing a 3, plus n effective times the energy density of one neutrino species, where, let me write, I should have written the energy density, so I'll just move that down. Okay. Oh, sorry, I see a couple of questions. Okay, question, but when the neutrino becomes non-relativistic, the temperature is not proportional to 1 over A anymore, right? False. The temperature, the momentum is always, what we proved last lecture is that the momentum is always proportional to 1 over A. And so that is equivalent to this temperature being proportional to 1 over A. So, like, what is temperature? The temperature means like I put a neutrino thermometer out there and I check like, oh, okay, so I guess there's 2 ways of phrasing temperature. One way of phrasing temperature is some sort of like thermodynamic argument where you have like a thermometer and you measure the temperature of some system which is having a lot of interactions. And those interactions give you this distribution. So the normal distribution a general one, let me step back. A general Fermi-Dirac distribution, instead of having P right here, would have E. And that would be the distribution for a system which is in thermal equilibrium. Once the neutrinos decouple, they are not in thermal equilibrium before. So this is just a distribution of their momentums, and this temperature reflects some measure of the average kinetic energy of the system. But I can truly think of this temperature as a parameter that describes the momentum distribution. Every P goes like 1 over A, and that is equivalent to setting T nu like 1 over A. If the neutrinos continue to be scattering off of each other while the universe expands, then no, then T would go like 1 over A squared, as it does for like a gas, which becomes a non-relativistic gas, which has temperature equal to, 3/2 kT is equal to P squared over 2m of the particles. Then the temperature would dilute more slowly. But that is, in this case, the way that I like to think about it is that everyone's momentum redshifts as 1 over A, and this is the distribution of the initial conditions. Okay, second question. Does the distribution we see today in the neutrinos depend on when they decoupled? It seems like as long as they decoupled relativistically, they have the same distribution, whether that distribution is enforced by thermal equilibrium or simply by a redshifted frozen out distribution. Yeah, so I think, I'm not sure if this answers the question, but I think I kind of answered this question before, right? So the relativistic Fermi-Dirac is a redshifted frozen out distribution is the way that I'm arguing to describe it. And that's why it looks like a relativistic Fermi-Dirac one and not, if I go out today and I look at neutrinos, the relic neutrino background, many, 2/3 of them are going to be non-relativistic, but this is still their momentum distribution. So this distribution depends on when they decoupled to the extent that because they were relativistic when they decoupled, this is the distribution they had. Another way you could put this is you could write this as at the initial time, you would have something like, you would have this, where this is E of P at that time over T nu. Actually, I don't want to write it down. You can, because it'll take longer on this than I want to. But you could write down the corrections to this distribution, and they would be of order the neutrino momentum, which is like MeV. Sorry, the neutrino rest mass, which is 10ths of an eV divided by MeV. Okay. Next question, isn't. Yeah, so no, let me repeat this. So you guys are asking the same question, so let me try to do it more carefully. Okay, so what I think, okay. Let me write this. Let me write this in one more way up here to try to address the question. So at decoupling, we have this E of P over T plus 1. And this is very, very close to E to the P over T plus 1, since M is much, much less than T decoupling. Okay, this is the initial distribution. And then I ask, what's the distribution today? I take every single momentum in this distribution and I redshift it by 1 over A. And that's equivalent to taking this initial distribution and changing T to 1 over A. That is a totally different function than if you just plug in E of P up here and let the rest mass dominate. The energy, when we go back and we compute rho, so this part here, the momentum distribution doesn't, the form of the momentum distribution doesn't change, but when let me move this down. When you compute the energy density at late times, then this is approximately just equal to E So when you compute the energy density, you're summing over all of them. You're asking what's the average energy over all of these momentum states. And at late times, the momentum is super small compared to the mass. So the energy is dominated by m nu, but the functional form of P doesn't change. Okay, last question. But if it decoupled at T decoupling was 5 eV or T decoupling is 5 keV, the distribution to us should look the same, right? Yeah, so if I understand Daniel's question correctly, it's just the statement is that the form of the distribution, it's relativistic Fermi Dirac because they decoupled when they were relativistic. And that doesn't specifically matter that it was, it doesn't have to be that nowhere in here enters the corrections that you would get to this equation here, which give like the initial momentum distribution would be larger if they decoupled later. But the form is the same. Okay, if we considered self-interacting neutrinos, different modes would interact with each other. And in this case, it could distort from the Fermi-Dirac distribution if those interactions were frequent and persisted until neutrinos became non-relativistic. I agree with that. So indeed, we don't have something that you could look for, or one way that you can modify the thermal history of neutrinos is to try to modify, is to introduce some interactions that modify this distribution function. And then you would modify the energy density of the neutrino. You could modify the energy density of neutrinos at early times, and you could modify their velocity distribution today. And indeed, there is work on that. So for instance, people who propose new sterile neutrinos, sometimes these sterile neutrinos could be produced through decays of other neutrinos, and therefore you would depopulate part of the Fermi-Dirac distribution, and that would lead to some distortions. At the moment, we have no measurements of the distribution function, but it's a fun thing to think about. Okay, so let me get through this last piece. So we can consider this to be the definition of an effective, which is from the cosmic microwave background, we can get measurements of the radiation density of the CMB, sorry, the radiation density in the universe at early times when we expect, assuming the simplest general relativity at very low energies. Remember, these are by particle physics standards, these are very low energies for new physics to happen. We get a prediction we measure the photon energy density. We have a prediction for the neutrino energy, for the energy density of each neutrino state. And then we can go out and detect, we measure contributions to the radiation density from neutrinos with this parameter. So there's a question, can you explain why T nu and T gamma? T nu is the temperature of the neutrinos and T gamma is the temperature of photons. I guess I didn't write temperature anywhere. Yeah, let me, okay. This, I mean, yeah, I don't know. These are the temperatures of these distributions. Okay, if the distributions distort from Fermi Dirac, can we still define the concept of temperature? No, you would have something else. So the great thing about a thermal distribution is that there's only one parameter you need to measure it. They're not in equilibrium today, so that's the point of this calculation. That's what this definition of decoupling was, is the neutrinos decoupling from the photons. That was the point of this calculation back here, is to determine the temperature at which neutrinos drop out of equilibrium from the photons. Okay. Okay, so this, if our calculation is exactly correct, then this N effective could be thought of as the number of types of neutrinos. Actually, let me put, the way I've defined 1 nu here, I'm going to put it 2 here, because N effective is actually defined as the number of flavors as opposed to neutrinos plus antineutrinos. This is, so CMB data gives current CMB data. Oh, let me comment one thing. So so 3 flavors, and so 3 flavors of neutrinos and antineutrinos would give an effective equal to 3 in the standard model. A more careful calculation, which includes the fact that E minus E plus annihilation heats neutrinos slightly because they are not perfectly decoupled, gives an effective for the standard model is equal to 3.045. So this doesn't have to be an integer because it's really just defined in terms of energy density. So if our calculation of the neutrino energy density is exactly correct, then that we could use this to measure the number of flavors of neutrinos. But our calculation, which it assumes that the process of neutrino decoupling was very separated in time from electron-positron annihilation, is not quite right. And more careful and very detailed calculations, including neutrino oscillations and so on, give a current standard model value of 3.045. The CMB, let me finish commenting on this, and then I'll come back and answer some questions. But I want to get to one more thing about how this can be used to test for any particle in thermal equilibrium before wrapping up. So current CMB data gives N effective equals, so via measurements of the radiation density, gives N effective equals 2.99 plus 0.034 minus 0.033, where these are 95% confidence intervals. And this is Planck CMB data from the Planck satellite, the compilation that includes this set of data, plus lensing, plus some data from WMAP, which they call low E, plus BAO, which I think is a beautiful confirmation of the standard model of particle physics. That this tells us that we know the energy density in radiation around CMB times, a little before CMB times, to better than 10%. We know the photon part almost perfectly, and then there's this neutrino part over here, and we measure that contribution to better than 10%, and at that accuracy, it agrees with exactly what we expect from the standard model. So that's great. Near-term experiments. Hope to get to a much more precise level. Okay, let me answer some questions, and I guess I won't get to say the next thing that I wanted to say. Okay, last question. So just to confirm, we conserve entropy at the E plus E minus decoupling time, define the temperature of the neutrinos today. So what we find, that's fine. So what we find at this process is the temperature. This gives us the temperature of neutrinos compared to the temperature of photons at any time after E plus E minus annihilation. So this is at any time after E plus E minus annihilation, including today. So since using, this is using T gamma equals 2.725 K today gives these temperatures today. But you could use this expression earlier. It's true at any time, but both of these, after E plus E minus annihilation, both of these temperatures, redshift is 1/A. Okay. Let me say, so I like this very much, and there are other ways of probing the existence of other neutrinos. Is n effective affected by the existence or non-existence of right-handed neutrinos? So this is that in order to contribute, in order for some particle species to contribute to n effective, whether it's sterile neutrinos, right-handed neutrinos, or something else, it could be axions or any other light relic particle from the early universe, it has to be contributing to the radiation density, because that's what we're measuring. So we define this parameter n effective, but we should always keep in mind that n effective is really defined as the radiation density minus the photon density divided by this energy density in one neutrino state. So something that is something like a heavy right-handed neutrino that's non-relativistic just will have negligible contribution to the energy density at early times and will not show up here. Sterile neutrinos, it depends on their mass. So what mass do you need? This is something that's good to write down. So note. So to contribute to an effective need to be relativistic at these times, which it depends on exactly how you want to compute an effective, but so this needs to be light, meaning mass is we want to say here. We want it to be small compared to an MEV. At CMB times, it's actually more like an EV. So the temperature of stuff when a CMB forms, it's around EV temperature. So it has to be super light. Sorry, this is not, yeah, that's what I mean. Right. And it doesn't have to be much less than, let's say, really dumb question. Does recombination not impact the temperature distribution of photons at all? That's not a dumb question. It does affect it, but very, very slightly. So there are so many, at the time of recombination, so there's like 10 to the 9 photons per baryon in our universe. So imagine, and then a good fraction of, we can just pretend that the baryons are all hydrogen, even though we have helium around. When hydrogen is formed, that of course emits photons of like 13.6 eV and higher order lines. Helium recombination also emits little photons, and that will make tiny, tiny wiggles on top of the CMB spectrum, but they haven't been detected yet. There are people who have experiments proposed to detect them, but none of, they're kind of small scale experiments that it's just too hard to do. And the reason that those lines barely affects the CMB spectrum is that there are so many photons compared to baryons. Okay, what constraints does n effective put on the Dirac and Majorana mass terms of the neutrinos. So I don't think ineffective puts any constraints on the mass terms of the neutrinos. Because this measurement, because this is coming from times, in order to contribute here, the particles need to be relativistic, and so the mass terms just aren't relevant. So to my knowledge, there's no relationship between this measurement and the form of the mass terms. Okay, sorry to step back to the distributions again, but is the CMB a blackbody distribution frozen out? This blackbody, is it frozen out as I was describing the neutrino distribution is frozen out, or not? And if I understand your question correctly, yes, the CMB, I was going to mention this slightly at the end of, during this lecture, but we haven't gotten there yet. But so the cosmic microwave background last scatters frequently at the surface of last scattering, which is the time when hydrogen atoms form. And then those photons have been traveling to us today without much interactions. Now, the actual form of the CMB momentum distribution was formed much, much earlier. So if I want to have a thermal distribution that's a black body, I need to have processes that can efficiently create and annihilate photons. So I can't have any chemical potential. I can't have, I need kinetic, to create a black body distribution, I need kinetic and chemical equilibrium. And the CMB actually, the kinetic and chemical equilibrium freezes out at redshift of like 60,000, well before the hydrogen recombination happens. So in some sense, the momentum distribution of the CMB is really inherited from redshift of 60,000. So following that, that's when chemical equilibrium drops out. The Compton scattering is inefficient at producing photons. The CMB remains in kinetic equilibrium, scattering off of electrons and so on, until redshift of 10 to the 4 or something like that, 10,000, and then today. So it depends a little bit on what you mean, but absolutely the CMB photons that are traveling through our universe are not interacting much. So I would again say that that's an inherited distribution from earlier times. Okay, I think I'm way over, so I will not continue on my next point. Is that correct, Andre?
You know, it's fine. I mean, remember you had this late start, let's say. But it might be a good time to stop so people can take a break and you can take.
I want to say one more thing, but I also don't want to fry everyone when they don't have a break. So they don't have a break before their next lecture. So I can